Hey everyone, I hope all of you are doing well today. What I have for you right here is a lecture on 6.2 in AP Chemistry, which is energy diagrams. This is a super short unit in AP Chemistry. It's just a few slides and just goes over a little bit of vocabulary that hopefully you learned in 6.1, and then it has a good practice problem at the end. So let's just go on ahead and jump in and see what it's all about. So this right here is just a list of topics that you should be able to do by the end of Unit 6. If you want to look over those, you can pause the video and then kind of look at what you should be able to do. But I'm going to go ahead and jump right into the next slide. So to start off, when we're talking about energy diagrams, I want to start off talking about what an exothermic energy diagram looks like. So what we have here is an energy diagram. And on this energy diagram, if you remember from Unit 5 in chemical kinetics, we start right here at reactants. And what happens is these reactants come close to one another. They collide with one another. And when they collide with one another, they have to get over this activation energy barrier. At the top, you have the transition state. And if you reach that transition state, you're typically going to go over the other side of the hill, and you're going to get down here to what is the products. But we're talking about thermodynamics, not kinetics anymore. So in thermodynamics, we don't really care about this transition state. In thermodynamics, what we care about is the start of your reaction and the end of your reaction, the reactants and the products. And what we're really caring about is this gap right here between them. You can see that the y-axis is energy, and so the gap between the reactants and the products, if the products are lower than the reactants, is the amount of energy that's released. And if energy is being released from a system, that means in our context, in thermodynamics, heat is exiting the system. Heat is leaving the system, meaning it is exothermic. It is leaving the system. The products then are lower in energy than the reactants. The opposite can be said for an endothermic reaction. Same reaction profile diagram right here, but instead of the reactants being higher than the products, now we have the reactants being lower than the products. So what you can see is there's a gap right here between them. That's how much energy is absorbed. And if you remember from our previous lecture, what that guy is right there, that is the delta H. That right there is the delta H for both the exothermic and endothermic reaction, the change in enthalpy, the change in heat energy at constant pressure. So it's really important in AP chemistry that you can look at one of these reaction profile diagrams and be able to determine really quickly whether something is endothermic or exothermic. You can also draw activation energy diagrams that look like this. These aren't as common, but you do see them. The usefulness here to somebody who's studying thermodynamics is these types of charts don't really focus on the transition state for things. All they're showing is that you have reactants right here, and those reactants have to break their bonds to become free atoms, and then those free atoms can come together to make new products. It takes energy to break a bond. That's the important thing about these diagrams. What we're showing here is that to break a bond, to break the things that are holding two atoms together, you've got to put in energy, and that's why you have a barrier right here. That's why you have a transition state. Once they're free atoms and they come back together to form new products, it releases energy. And if you release more energy than it took to break the bonds, you're overall an exothermic reaction. If you have to put in more energy to break the bonds, then you release to form products, then what you have is an endothermic reaction. And that's what these types of diagrams are just trying to show. One other thing I'll mention, and then we'll do just a quick practice problem. We talked in Unit 5 about catalysts and how catalysts increase the rate of reaction. And the way that they do that, if you look over here on this diagram, is that they lower the activation energy barrier. So you have an uncatalyzed reaction right here that has a pretty tall activation energy barrier. It takes a lot of energy to get up to that transition state. But right here, if we catalyze that reaction, then it doesn't take all that much energy. So these reactions end up going faster. An important thing in thermodynamics that I really want us to highlight is this point right here. Delta H, the difference in energy between the reactants and the products, is never changed by a catalyst. A catalyst just gives us a different path to get between the reactants and the products. it doesn't do anything to the delta H. So don't ever say in any of your free response questions or anytime you're trying to talk about how a catalyst changes a reaction that it changes anything about the reactants or products. All it does is change the path. So in thermodynamics, catalysts, we don't talk about them very much other than the delta H is just not changed. So having said all of that, let's do a practice problem together really fast. So this practice problem says, consider the reaction. We have two molecules of ClF3 and 2 molecules of ammonia, NH3, reacting to form a molecule of N2, 6 molecules of HF, and 1 molecule of Cl2 with a delta H of negative 1,196 kilojoules per mole for the reaction. What this wants you to do is draw a reaction pathway diagram for this reaction. Label the products, reactants, and delta H. So we did this a lot in Unit 5, for those of you that are my students. So we did this a lot. So you should be pretty comfortable with drawing a reaction pathway diagram. So I'll just go on ahead and start with this one. So to draw a reaction pathway diagram, first thing we're going to have to do is we got to put our axes down. Our y-axis is going to be potential energy. I'm just going to label it as energy for right now. And our x-axis over here is reaction progress. Reaction progress. And what you're going to see in these videos is my handwriting is terrible. So it's reaction progress. Our reaction overall, what I want to highlight here is that our reaction overall is exothermic because heat is leaving the system. What that tells me is my reactants are higher up than my products. And we don't know how many, transition states there are, but let's just say that we've got, one transition state for our reaction here. Our reactants are higher up than our products. So the reactants are right here. The products are right here. The delta H that we need to label is the difference between the energy of the reactants and the energy of the products. That's the delta H right there. Okay? So if any of that's super confusing, feel free to leave me any sort of comments below. I'm happy to answer any of those for you. And if there's any other questions, you can also find my email and you can just send something to me there. I hope you guys have a great rest of your day, and let's come back and do some chem next time.